time to start. It's a pleasure for me to introduce Eugenio Coccia, was director of the Gran Sasso laboratory under the mountain in Italy. Some of you is there.
The others message have the mic.
Right, I was saying it's a pleasure to introduce Eugenio Coccia. He was director of the Gran Sasso laboratory for 6 years, then director of the Gran Sasso Science Institute. This is an institute in L'Aquila in central Italy. We devoted mostly to astroparticle physics. And now he's director of the High Energy Institute in Barcelona, Spain. Eugenio is very well known all over the world for his work on gravitational waves, on the developing of detectors for gravitational waves. And I want to read to you the motivation for a prize that he received recently for his major contribution to the realization of the first long-term observatories with cryogenic and ultra-cryogenic detectors of gravitational waves, and for his international role in the gravitational wave community and in the broader community of astroparticles. So we'll hear today about this new enterprise in Europe, the Einstein Observatory. And without saying more, I'd like to welcome Eugenio to the talk.
Thank you, Francesco. It's a pleasure to stay here. I hope that people can hear me, even people online. I hope so. And let me start my presentation with this movie. This is the Einstein. This will be the Einstein Telescope. You see, it's a triangle. Louder, okay. It's a triangle underground with many tubes. You see this strange structure with the people around looking. It seems to know what they are doing. What is this? Why we think this is a very important project for the future? Is the microphone volume? Okay, I will. Is that better? You feel better? Okay.
You should keep it fixed, otherwise.
Yeah, I think you want to pin it. And share the screen on Zoom. It doesn't seem to be the comment just said that it's not shared.
That's beyond my paper. Okay, I don't. It's better.
Yeah.
It's okay. Can I try to? Okay, no, it was me. Okay. So let me explain, if you hear me. Let me explain why we think this Einstein Telescope, this triangle which we've seen with vacuum tubes underground, with some cryogenics, some vacuum, what is this? Why we think it is important? And to understand why it is important, we have to understand why it is important to detect gravitational waves in all the universe. This picture is taken from the Hubble telescope. Is a far view of the universe. You see electromagnetic waves basically, and there are all a range of electromagnetic waves. The visible is only a window, but there are many detectors on the Earth, in the sky, that investigate these electromagnetic windows in all the wavelength, discovering, of course, studying how the universe is made and many, many sources. So gravitational waves is a totally different thing. Is another messenger. The gravitational waves is complementary completely to electromagnetic waves, as a vibration of in the space-time, traveling the speed of light. This is in common with electromagnetic waves, but there are many, many differences. And to appreciate even a future detector, let me review what is gravity in the Einstein general relativity. Gravity is manifestation of space-time curvature induced by mass energy. You see here that this G is the geometry of the space-time, and this is the content of matter and energy in the space-time. This is a constant, which have very interesting features, but this is the symbol which is the most important. I mean, that space-time curvature depends on the content of mass energy. This is the basic information. There is no space, time, and gravity. There is space-time curved by the presence of matter and energy. In a statement from Wheeler, which I will show in a moment, in this picture I show the difference with the Newtonian gravitation. There is a mass, say the sun. There is a gravitational field around because of this mass, but the space-time is flat, is Euclidean, there's not interaction, let's say, between the geometry and the presence of matter and energy. Following Einstein theory, there is no gravitational field, really. But gravity is a manifestation of the fact that the presence of matter and energy deforms the space-time. And this is the famous statement, space-time tells matter how to move, matter tells space-time how to curve. Sir Archibald Wheeler. So one other thing that is important to understand gravitational waves, and is never reported, to my knowledge, is that the space-time is the stiffest medium existing. In fact, it is easy to see that if we compare the equation of Einstein, this is the geometry we said, it is the cause, why the geometry is changed. We can compare this with a simple equation of a spring and a force applied, where this is the elastic constant expressing how stiff is the spring. So this is the geometry. This is the driving term, let's say, and actually we can compare this with the presence of mass and energy, and this is the geometry. So at the end, it's like if space-time has this stiffness. The stiffness is an enormous number because C is large and G is small. At the end, it is 10 to 45 kilograms per second. It's the stiffest thing you can imagine. This means that even if the wave amplitude is small, the energy associated is enormous. It's enormous. So it is difficult to detect because of this, because do not interact with matter, let's say. This is the problem. But the energy associated with gravitational wave is very large. So gravitational waves are a consequence of the general theory of relativity with the weak field approximation. the equation which I showed before, which is a complicated equation, nonlinear equation, it simplifies, becoming the D'Alembert equation for wave propagation. And the gravitational waves happen to be a perturbation of the space-time. If it is small, the perturbation respect to a flat space-time, then it propagates with the speed of light like a wave. And it has features which are totally different from the ones of the one of electromagnetic wave, because it is true that there are two transversal polarization states, but this is associated with massless spin 2 particles. And so the geometry of the wavefront is totally different. The effect is this one. This is the effect on the space-time when the waves travels. Is a typical tidal force, and the amplitude given by a system, if we see the energy lost by a system, moving system, there is no dipole term in the expression of multiples because of the conservation of total momentum in the system. So the first non-null term is the quadrupole. So this means that you need a quadrupole component, L equal 2 component for generating gravitational waves. Einstein himself tried an example at the time, I mean 1916, with if it was possible to generate gravitational waves in laboratory, like Hertz did with electromagnetic waves. So he imagined a very big cylinder of steel, many meters long, 4 meters diameter, rotating at 4.5 Hertz, limiting frequency to not break the cylinder. And the energy lost by the system was so low, so ridiculously low, that the comment from Albert Einstein in his paper was that in any case, one can think of A, the amplitude, will have a practically vanishing value, a practically vanishing value. So do not try to detect. Well, Einstein didn't know at the time of the existence of such a violent universe we have today. He didn't know about neutron stars, about stellar collapses, about black holes. So even if there are consequences in some of these equations, but the universe was very much more calm at that time. So the idea that there were sources able to generate gravitational waves very important was practically without hope. There were many years before the first attempt to detect the gravitational waves, and let me say that as is known, Einstein himself had doubt about the existence of gravitational wave, or not the existence, the detectability. If these waves were an artifact of the coordinate and not real wave changing possibly a material system. The question was debated with many contributions about sources, about the waves, but at the end, in 1957, in Chapel Hill, there was a meeting. This is where the gravitational wave detection attempt started. In Chapel Hill, there was a meeting in which such a huge amount of people, Bergman, Bondi, DeWitt, Bob Dicke, Feynman, Misner, Pirani, Wheeler, also Joe Weber was there. They tried to understand, are gravitational waves detectable or not? And this simple paper, 2 pages, 1.5 page actually, from Pirani, was the key point that convinced everyone that gravitational waves were actually detectable. The reason was simply, I mean, the gravitational waves stretches the space-time. It must have an effect. If you have 2 points with a spring, then at the passive gravitational wave, this spring has absorbed energy. Or if you have 2 mirrors and the light going back and forth, when the wave passes, you can detect a different time from back and forth from these 2 mirrors. So it convinced with very simple arguments that gravitational waves were actually detectable. Joe Weber was the first to actually try to detect gravitational waves. As you said, I said that there are no laboratory equivalent. The luminosity for a mass of m and size r, say oscillating a certain frequency, is a very small number. In fact, with the 1,000-ton steel, Einstein had this 10 to the minus 30 watt of energy. But now we know that the collapse to neutron stars gives a very different amount of energy. So the comment of Fairbank, Bill Fairbank from Stanford was one of the first to try to detect gravitational waves after Weber, a challenge for contemporary experimental physicists. So it's not impossible, it is a challenge. This is what changed the mind of the people. But how was it 10 to the minus 18 meter, for instance, which the estimates for a typical events in our galaxy? At that time, people thought to supernovae. So 10 to minus 18 meter was a typical figure one was to fix to try to see how we can measure something with change of 10 to the minus 18 meters on 1 meter. Well, if you take a human hair, this is 10 to the minus 4 meter. If you divide the human hair by 1 million, you have the atomic diameter, 10 to the minus 10. If you divide the atomic diameter by 100,000, you have a nuclear diameter, 10 to the minus 15 meters, Francesco, more or less. And if you divide the nucleus by a factor 1,000, then you have 10 to the minus 18 meters. So you should be crazy to try to detect such a thing, okay? Well, in fact. But the reward was terribly good, terribly high. This is why it was a challenge. Because, of course, the objective were, first of all, to have a first detection to demonstrate that the general relativity is correct even in this dynamic prediction. Then there is a motivation coming from astronomy and astrophysics, because the sources of gravitational waves are sources which are dark even, like black holes. You cannot see by light or electromagnetic waves. And then also there is a cosmological reason, because photons decoupled from primordial plasma when the universe was already 380,000 years old. Neutrino decoupled when the universe had 1 minute, more or less. Gravitational waves decoupled to 10 to the minus 34 seconds. So it is the message, the most pristine message that we can get from the Big Bang. So for all this reason, it is important, the gravitational waves, that we say that it cannot be a symmetric source, because there is no quadrupole moment, should be something which has some asymmetry, non-axis symmetry in particular. So for instance, 2 stars rotating one around the others, for instance. So even pulsars, but which such a small amount of non-axis symmetry. The statement from Kip Thorne, gravitational waves can reveal features of their sources that cannot be learned by electromagnetic, cosmic rays, or neutrino studies, is correct, because see, electromagnetic waves are emitted by incoherent superposition of many elementary acts, while gravitational waves is emitted by a coherent movement of a big body. And in fact, the information you can get from various sources, each source has its own waveform coming coming out and arriving to the Earth. You can get a burst from a supernova and then understand the inner detail of the dynamic of supernova, see neutron stars and black holes being formed, and knows about nuclear physics at high density. For the spin neutron stars, for instance, and pulsar, you can get information on neutron star formation, neutron star physics, basically the equation of state, and on the pulsar evolution. From coalescing binaries, which is a system of two stars rotating and emitting gravitational waves, losing energy, and then rotating faster and faster to conserve angular momentum, at the end merging with each other, you can get the masses of the object, you can identify black hole clearly, you can measure the distance to the system, and also the Hubble constant, because you can have a standard candle, like two neutron stars coalescing, and the standard candle, the amplitude gives you directly the distance to the source, independently from the redshift. So this is why it is also important. And then, of course, the stochastic background maybe is the most important thing, but the most difficult to detect. You need two detectors which are coherently forced by the stochastic background. Detectors should be not so near to have common sources of noise, not so far to have that the waves are not such bandwidth large, but however, it is will be really rewarding. So comparing with electromagnetic waves, I already shown the fact that respect to electromagnetic waves, the polarization of the gravitational wave is different. It is the same, the two polarization, one rotated 45 degrees respect to the other. This has to do with the spin to nature. This has to do with the fact that there is not two opposite sign for gravity, not plus and minus like an electromagnetic wave, this is only attraction. So all that are connected. I like this statement because I like things which people do not know, or at least which surprised me. So Lord Kelvin, which was a celebrity and a very big man, of course, said about the electromagnetic waves, it seems to me that it is rather a backward step. The one thing about it that seems unintelligible to me. I do not think it's admissible that there should be an electric displacement perpendicular to the line of propagation. So for Lord Kelvin, the fact that electromagnetic wave means electric field perpendicular to the line of propagation, this was, for instance, crazy. Because like sound waves should be, the propagation of the signal should be or in the direction of the wave. So I think, okay, however, in going rapidly now, to detect gravitational wave, you will be able to detect a passage of something which moves like that, a system of particle in a circle, for instance. And then two methods were imagined. One is a laser interferometer, a Michelson interferometer, in which gravitational wave acts contracting this, elongating that, so that the interference there changes. I will show you that better in a moment. So here, the change, the amplitude of gravitational waves directly proportional to the variation in change of the arms. The other method is to consider an oscillator in which gravitational wave is practically a driving force, like a hammer hitting on a harmonic oscillator and then putting in vibration this. This was the method originally put in action by Joe Weber with the cylinder, you see, with the piezoelectric ceramic glued on it. They transformed the mechanical vibration into electrical signal. And so you know if something arrived, a sort of diapason, if you want, resonating at the arrival of the gravitational wave at its resonant frequency. He didn't succeed. However, he published to succeed, but it was not true. I mean, because there was no one else found his results. So the moment in which I entered as a PhD student in this field, there were a new Weber type detector, 10,000 times more sensitive. Why? How? By cooling the bar to very low temperature, by applying superconducting transformers, transducers to reduce thermal noise and electronic noise. And so we are here. This is Edoardo Amaldi. And this is Explorer at CERN. This is Nautilus in Frascati. This is Auriga in Legnaro near Padova. With this gravitational detector, we had a jump in sensitivity, but again, we did not observe signals. So after many years of attempts, we arrived to another kind of detector, which was developed in parallel with the resonant bars, but it was clear at the beginning of this century that this was the right method, the larger bandwidth and the demonstration actually of the feasibility and of the fact that they worked. This is LIGO, one of the LIGO in US. This is Virgo near Coccia. And so this was the method actually with which we can detect something like 10 to the minus 18 meters. So the method is very simple in concept. I show this. This is not a Weber bar. This is the laser. This is schematic, very schematic, of course, picture. This is the laser. This is a beam splitter dividing the beam of the laser in two. One goes in one arm and reflects back. The other is transmitted and reflects back in the other side. So they arrive here, and part of this go to the detector. Of course, it goes the interference between the two beams. Since it is better to show an animation, this is the laser going in the two directions, and you see now the two detectors are chosen with the distance such that the waves are negative interference, but if something moves, of course, the interference becomes positive. So this is the laser light going to one mirror and to the other. They interfere. Now, suppose the interference is negative, so you have no light at the detector. But if gravitational waves arrives, one arm is longer, the other is shorter, of course, changing with the frequency of the gravitational waves. And so you see that there will be a spot on the detector changing with the frequency of the gravitational waves and with the intensity proportional to the amplitude of the gravitational waves. This is the detector. It's much more complicated than that because there are many sources of noise which we have to fight. There is the seismic noise, Newtonian noise due to the masses around which moves, radiation pressure, the laser noise, of course, there is noise at the photodetector, the shot noise. So you have to fight very hard and not only, but try to employ all the energy inside the detector. So to put, for instance, a power recycling mirror, so the light which goes back go again inside. And at the end, you find something which is to optimize which you have to, you cannot buy on the catalog things. You have to develop in the laboratory very special things and non-existing at all. And this is one of the driving for technology and innovation. Basic science is the driving force for technology and innovation because there are new questions and you need to develop new answers. The three basic sources.
Very basic question. So the wavelength is going to be in the optical, I suppose. So it's 10 to the minus 10 meters. So to go to 10 to the minus 18 meters, does it mean I need to be able to measure the phase of waves at 10 to the minus?
No, okay. The wavelength of the gravitational waves is one thing.
I'm talking about the wavelength of the
wavelength of the laser is another. The wavelength of the laser is very small, it's angstrom. The laser of the wavelength of the gravitational wave is hundreds of meters, the wavelength. For 1 kilohertz is 300 meters, the wavelength.
So I'm talking about the displacement of the mirrors. It's about 10 to the minus 18.
Yeah, no.
doesn't mean that I need to be able to measure phase information of my.
Yeah, you measure the phase information and you measure something in a system which is smaller than the wavelength which arrive. So all the system is put coherently in vibration. Let me go on, maybe I can explain better this fact. I want only to show you the three main sources of noise. At low frequency, you see, this is the frequency range for this kind of detector, from few hertz to the kilohertz. Here you are limited by the seismic noise, which is terrible. Below 1 hertz, of course, it's impossible to have an Earth-based detector of this kind at the Earth, on the Earth. In the middle, there is mainly the noise from suspension and test masses. This is in part, great part is thermal noise, which you can fight with the appropriate material, of course, and cooling down the system. And that at high frequency, this is mainly the shot noise from the laser. To reduce that, you should have high power lasers. So all these have been developed, and the 2 LIGO detectors in the US were able, on the 14th September 2015, to detect the first signal. This is the noise in the detector in Hanford. This is the noise in the detector in Livingston, Louisiana. And this is the noise. See? At a certain moment, it arrives something which is a typical wave from a coalescing binaries, and the same waveform in the other detector 3,000 kilometers away. So if you subtract the noise, you see the identical waveform. This is the sweeping in time versus the frequency. You see the amplitude is larger and larger, and the frequency also is larger and larger. And this is the typical sweep of the signal. This was the first signal detected. It is incredible the information that you can detect. You can have from a very small, a very short time, a wave. This is less than half a second, few tenths of a second. And then with this simple waveform, you know that one mass was 29 solar masses, the other was 36 solar masses. The distance was 1,300,000,000 kilometers away from the Earth. You can wonder how you can extract from a simple waveform all this information. Well, this is because we have many examples of the system assuming general relativity. And so from the waveform, you can extract all this information. For instance, what I say is usually in the talk with general public, if you enter in a black room, dark, you don't know what there is inside, and someone plays a note on the piano, pling, you know from something which lasts for less than 1 second, you know that there is a piano. You know where, because you have 2 ears. You know which was the note, if you have educated in music. And if you have educated really on the piano, you can even distinguish if the piano is a good or is a medium or is a bad. So it is incredible, the information that such an instrument like our ears can detect from a wave. And this is not, with this example, you can understand that due to the many waveforms we have in the system for simulating the various kind of sources, we were able to distinguish the oscillation, the phase in which there is the merger, and even the post-merging oscillation. The speed of the masses at the end, just before merging, was half the speed of light. You can imagine 36 solar masses going half the speed of light. And the total mass at the end was not the sum of the two mass of the black holes, was emitted most of that in the final phase, 3 solar masses in energy. This is the largest conversion from mass to energy we never assisted. In that moment, the energy emitted by this system was more than the entire electromagnetic energy emitted by the rest of the universe. This is why the black hole is a fantastic object, of course, but also the space-time is so stiff. So, and this was an example of a simulation of what it had been happened. Maybe you have seen this several times because, of course, we celebrated the detection of gravitational waves in many, many occasions. This is much slower than the real, but there are two black holes in this reconstruction which danced one around the other, and that we fused by eating each other, let's say, without no photons, no lights. So these things are two monsters, 26 solar masses, 29, 36 solar masses, but the dimension is a dimension of 200 kilometers. It's the dimension of a small county in here. So there are two things which is incredibly small at 1 billion light year away. You never could have seen this. You heard this by the wave which arrived. I think this was really an achievement for experimental physics, let's say, but I think for the Homo sapiens, actually. So this is the reconstruction made with the simulation in which it's clearly you see the crest of the wave, the peak of the wave. This is the moment in which the peak is emitted, and it traveled for more than 1 billion years through the universe, arriving at the Earth. So emitted when there was a very simple life, the Earth, and arriving on 14th of September. Also, the Earth have reacted to the arrival of gravitational waves, not so much. Lucky, this is just to show that the interaction, even as elastic sphere interacts with gravitational waves. However, this was this time there were detectors sensitive enough to detect gravitational waves. Glory, glory, hallelujah! Nobel Prize for the three fathers of the system. The server of particle review letters crashed because of the number of download of this paper. Okay, everyone happy. So there was a global network. LIGO was the first to take data, then LIGO after 2 years, and together they detected many, many more sources. This is the system. This is the 2 LIGO and the Virgo detector. I should show you also. And the Virgo detectors in Coccia, which is there near Pisa. Okay, so at the end, we not only detected this very big event, but many, many others. In blue, you see here all the merging of black holes detected by LIGO and Virgo. In orange color, you see the neutron stars, the neutron star binaries or neutron star black hole binaries detected by LIGO and Virgo. This in yellow and this in red were the neutron stars known by electromagnetic detectors and the black holes known to attract matter from another stars and so to give electromagnetic waves. So you see the huge amount of information, the huge jump that we had. Then we had another big jump on 17 August 2017. This is when Virgo and LIGO both detected the arrival of a wave, and this time were 2 neutron stars, not 2 black holes. So light was emitted actually, and was emitted in a way that was very interesting. This shows also the use, the importance of this detector, because LIGO and Virgo detected a signal. There was an alert system for alerting all the telescopes on the Earth, electromagnetic telescopes, from radio to gamma, to point in a certain direction of the sky, because the triangulation, the arrival time of the gravitational wave on the three detectors manifested in the sky as a region where something were happening. You see, something were happening. And with this something were happening was observed for in the hours after the alarm, with the region of the sky indicated by LIGO and Virgo. And these are, is a reconstruction of real data. So these are the images from various telescopes in Chile and the other part of the Earth. So observing deeply, they have individuated a certain pale signal coming from that galaxy. And this system, these are real data. This was the real color coming from this merging of two neutron stars in time. So we were attending in real time the fusion of two neutron stars. Not impossible without the indication of the gravitational wave detectors. So this was the brightness in the days after the event. It was very hot, evidently, the two nuclear objects fusing together. They had this, in the day, they have individuated some lines, you see? These lines are the lines of the nucleus of heavy elements formed in that part of the sky. And actually, from that single event, we know that there were formed gold, tungsten, uranium. For instance, for what regard the gold, which is something which is always nice to say, the amount of gold formed was 100 times the mass of the Earth in gold. I can try to go there, but it's very far. So what is important is we understood that the element formed by the merging neutron stars are all the elements indicated here in yellow. This was a breakthrough. So monumental success, let's say, of the advanced detector, the Advanced LIGO, Advanced Virgo, the so-called second generation. So the success regards the first detection, of course, the first detection of a binary system, so the birth of the multi-messenger astronomy, demonstration of the localization capability, the measurement of the gravitational propagation speed. We see that the waveform arrived in all the component frequency at the same speed. So we had an upper limit to the mass of the graviton, an upper limit to the speed of light, 10 to the minus 15, 10 to the minus 22 electron volt for the mass of the graviton. So very, very stringent limit already with few signals. An alternative method to measurement of the Hubble constant, and we have seen that gravitational waves are the one, at least within the precision of the measurement, are the one predicted by general relativity. Is all done? No, it's not all done, because we have seen only sources by a limited part of the universe. Of course, all the field took a boost and also self-confidence for realizing future detectors, for improving the present detector. But the present detector have a limit. They are infrastructure for LIGO 4 kilometers long, for Virgo 3 kilometers long. We need to change the infrastructure to get the most of the sensitivity and to arrive to see very, very far. For instance, with Advanced LIGO, we arrive to redshift, which are quite limited, you see, and this is the total source mass frame for the for the mass of the coalescing binaries, but we can go in a jump, a terrible jump, and go to redshift, cosmological redshift, let's say, with future detector. But we need to realize different infrastructure. We can, with the two projects, one in the US, Cosmic Explorer, and the other in Europe, Einstein Telescope, we want and we can have a jump of factor 10 in sensitivity. 10 in sensitivity, in the amplitude sensitivity, means, since the amplitude goes like 1 over the distance, 10 in sensitivity in amplitude means 10 to the 3 in volume of observable universe. Since roughly this is proportional to the number of sources, this means a factor of 1,000 in rate of events. We now have 1 event per week. We could have 1,000 events per week and discover also possible surprises. So this is the Cosmic Explorer. It is intended in the US to be a 40 kilometers interferometers on surface. There is a possibility to have 140 and 120 kilometers, but basically this is a factor 10 in length, which give you the jump in sensitivity. The other is to have is the European way, let's say, which you cannot have 40 kilometers nowhere in Europe, free from people and cities and villages and similar like this, mountains and so on. So the idea was to have a shorter interferometers, 10 kilometers, but underground, and I will show you in a moment why underground, and cryogenic. This is the facility of the Einstein Telescope. So it is underground because we need to reduce seismic noise and Newtonian noise. The Newtonian noise is fundamental at low frequencies. The limiting factor at low frequencies, in fact, is simply due to the fact that the force of Newton felt by the mirror goes where the mass is more near. So it is you need to go underground to get rid of this kind of noise, which is the limiting noise at low frequency. It is important to go to low frequency for make astronomy. Going to low frequency means intercepting the coalescing binaries in the first phases, let's say, so be able, have more time to say to the telescope where to see and to follow the full event. This is one of the reason why we have to go to low frequency. Not only, of course, there are pulsars also, which you can discover. So the idea is to have sensitivity at low frequency, but also sensitivity at high frequency. Those are, in a way, conflicting. Sensitivity at low frequency means underground, of course, but also cooling down the mirror. Sensitivity at high frequency means high power laser, but a high power laser is a source of heat for the mirrors. So it is in contrast with cooling down the mirror. So we need to have a set of 3 + 3 interferometers in the same laboratory, which cover the entire sky. 3 are for high frequency, 3 are for the low frequency. And there are different kind of properties, of course, different kind of masses, different kind of lasers. One is cooled and the other not. At the end, the result is, however, to have a combined sensitivity for the triangle, which is this curve. So going from few hertz, let's say, up to the kilohertz, and with a much better sensitivity. This translates with a sort of other properties. For instance, we can combine the output of the 3 interferometers to have a null stream. So to understand that the excitation of the system is a tidal force, a spin 2 excitation, not a source of noise, for instance. Was a long path from the idea to the concept design report. In the meantime, the detector became a proposal for the European Science Forum for Research Infrastructure, and was approved in a first, let's say, preliminary phase to arrive to the technical design report. The sensitivity is so good that for binary black holes, you can arrive to a redshift such that in that part of the universe, there were not the stars yet. So if you detect a black hole merging at that distance, this means that they are primordial black hole made of energy, not made of matter. I mean, originated not from collapse of stars, but from fluctuations in the primordial part of the universe. This is the science in a nutshell. This is the cosmological redshift at which you can arrive, and this is the mass involved in the system with the different signal-to-noise ratio. I mean, now to show better this, the difference also between Cosmic Explorer and ET, you have the same graph there. So the Cosmic Explorer is better for small masses, but then ET becomes better for larger mass, because larger mass means low frequency, and low frequency is better, the Einstein Telescope. This is respect to Advanced LIGO. You see, this is a very elementary detector, even if it is a miracle detector, but it's the very elementary respect to what we want to realize. The science case is full of astrophysics motivations and of fundamental physics and cosmology. I think the best I can do is to leave you the slides for appreciating calmly all these things. In addition to that, of course, there is to expect the unexpected. There will be the third generation Cosmic Explorer and the Einstein Telescope will be fantastic for multi-messenger analysis combined with electromagnetic detectors, because they can do many things. They can understand nuclear physics, they can understand nuclear synthesis, they can understand the origin of gamma ray burst and many other things. They can impact the probing the structure of neutron stars, because the structure of neutron stars at the end of the merging, there will be a vibration of the normal modes of the things which remains, which reveals if the material is stiff, is soft, there is no way of testing nuclear physics in such a huge amount of, in such a macroscopic object at this kind of density, What more? Something more. Yes, the localization, for instance, the localization up to now arrived because of the signal. You understand which is the position of the source by the delay in time. With the triangle, with the ET, it is different, because since you are sensitive also to low frequency, you have time for several rotations of the Earth for understanding the source, where it is the source. In the three interferometers can detect, of course, a different part of the excitation because of the rotation of the Earth in the meantime. It's the same kind of mechanism for which LISA, for instance, the space detector, can detect the position of the binary stars. So the localization capabilities also are much better, of course. And this telescope, this project is in the roadmap of the European Science Forum research infrastructure. In Europe, this means having money for the preliminary study, but also being in a roadmap of the future research infrastructure, which must be realized, So this is the current organization of the project. We have a structure with the observatory and the collaboration structure similar to what the LIGO observatory has, with the intervening, of course, the agencies and the governments. The cost is around, let's say, $2 billion for the detector only. Part of that, major part of that is the infrastructure, the excavation, vacuum tube, all the infrastructure system. I am the chair of the collaboration board, and I can tell you that there is a lot of interest. The other groups of the collaboration are not only in Europe, are also in other parts of the world, including in the US and South America. So this is the place. One is Sardinia, the possible place for this triangle. One is Sardinia, because Sardinia is a very quiet place seismically, one of the quietest in Europe. And also the population is very low. It's not anthropization, let's say, very low. So it's a very good place. Another is in this region, which is at the border of Netherlands, Belgium, and Germany. And another is in Saxonia, but this is not yet recognized. I mean, while the Italian government and the Dutch government have committed for 1 billion euro if the detector is made in the country, Germany is still thinking what to do. So let's say that these two, we are investigating the features of these two sites for the detector. There is also another parallel study, which is not one triangle, but having two L. For instance, one in Sardinia and one in Netherlands. The total cost is a little bigger, not so much because the excavation for 6 interferometers, like in the triangle, is much more large excavation than for L-shaped detector. And having two detectors is also gain in source identification, but you pay in the system in the sense that you need working to side, you need a stronger collaboration, let's say. The timeline is such that we count to be in 2035, more or less the same time of LISA in data taking after all these steps. This is maybe optimistic, but you always start with optimism. I give you with pleasure the links for some Einstein Telescope, which you can find and you can see. Let me say that for gravitational detector and sources, this is the general situation. Even better, let me say this is the same, but is more clear. This is the part which is investigated by Earth-based interferometers. This is a part where there is the nuclear physics, fundamental physics, neutron star, black holes being investigated. This is LISA, which is more for supermassive black holes, slow system, larger system, and for binaries far from the coalescence, let's say, also for the possible stochastic background. Then there is the pulsar timing array, which however study electromagnetic waves, how gravitational waves modulates electromagnetic wave of network pulsars. And then of course there is the imprint on the cosmic background of the primordial gravitational waves. So this is my last slide. Every newly opened astronomical window has found unexpected results. This was true since the time of Galilei. We was not expecting, looking with the telescope, looking Jupiter to find satellites. which breaks the crystal sphere of Aristotle going around. It was a breakthrough for human culture, I think. But no one predicted pulsars. No one predicted the gamma rays coming from the sky and not coming from nuclear tests from the Earth, and also the cosmic micro background. So every time astronomical window has been opened, the best thing were not predicted, let's say. And now we are just at the beginning. Just open the window. You see, you're not open fully. You will open fully with third generation. But just already now, we have seen many more black holes. Before the first detection, it was not clear if it was possible to have two black holes which meet and coalesce in Hubble time during the life of the universe. And now we have seen hundreds of this system. Where they come from? Even with masses, which is hard to explain as a result of a stellar collapse. Mass of hundreds of solar masses. So it is just the beginning of a new adventure. Thank you for your attention.
All right, I thank you for a really nice comprehensive.
Jennifer told me to give you the microphone. Not only to you, because there are people online which otherwise.
Thank you. Now they can hear me. Okay, so
Say again.
thank you for a beautiful talk.
Okay,
Yeah,
thank you.
yeah. Let's not miss that part. I understand the value of increasing the length of the arms of an interferometer, but why can't you do this just with reflections? Why can't you just have, instead of going from 4 kilometers to 40, just have many, many more reflections?
No, in fact, there are many more reflections. I mean, the signals accumulates, and in fact, there are Fabry-Perot cavities where the signals enters and go back and forth many times, hundreds of times, in part every time coming out. No, one part is coming out. So the signals accumulates many more times, and the effective length is much more than the 3 kilometers, because the signal accumulates many times during the back and forth travel of the light. This is true.
Prevent many more reflections still.
Well, the limits is the storage time of the photons in the system, which then limits your bandwidth. You see, so you cannot go. You lose at the end because this is the limit.
So I want to repeat the question I asked earlier.
Yeah.
So
we didn't understand fully before.
Right. So you want to measure a strain of about 10 to the minus 18. So displacement of about 10 to the minus 18 meters. You're shooting light with a frequency of 10 to the minus 10 meters back and forth, and you're correlating it, okay? So what that means is that you're trying to measure a phase shift in the light of 10 to the minus 10 meters of 10 to the minus 8. So how do you do that? I mean, that baffles me that you can measure a phase shift of 10 to the minus 8.
This is what we, research in the field, says. It is possible. Well, one reason is that this is not a movement of a particle. It's a movement of coherent movement of a solid body. Okay, and the sensitivity, because of the accumulation of the signal in the system, and because of the sensitivity of the photodetector, is such that you arrive to the sensitivity. You have to multiply for all the reflection back and forth because the signal accumulates. And so you arrive to detect a difference in phase shift, which corresponds to this kind of displacement.
So there was a bullet point that stated that the Einstein Telescope would be able to detect both polarizations of the gravitational waves. And I think I might have missed a discussion as to how it would do that. Do you mind explaining?
You can do that by combining the output of the interferometers, which are not exactly parallel one respect to the other, you see? So the two LIGO are almost parallel, but Virgo is not parallel, cannot be, because the surface of the Earth cannot allow this. So by looking to the proportion of the signal in each detector, you can arrive to understand the polarization, to distinguish the polarization. Now it's very rough with the present detector. Will be better with the Cosmic Explorer and with the triangle. Well, already the triangle is more understood because there are actually, for each low frequency, high frequency, there are 3 interferometers. So it is clear that combining comparing, let's say, the output of the 3, you can arrive to distinguish the amount of polarization that there are.
Thank you for the great talk. I was just curious about what are the differences between the Einstein Telescope and the upcoming LISA mission? Is it mostly frequency or amplitude or both?
Yes, in fact, I should stay in the slide more time in the previous slide, but the frequency range of LISA is completely different from the one of the Einstein Telescope, actually. They are not overlapping at all. In fact, let me show you in a moment. You see, LISA is in the region 10 to the minus 4 hertz, well, with a large bandwidth, actually 10 to the minus 2 to the minus 4, while this is 10 to the minus 2, few hertz to 10 to the 4. So they are not overlapping, the two, and this means that the sources are different, but in part will be common, in the sense that think to a coalescing binaries. When it is far from coalescence, it will transit in the bandwidth of LISA, and then after maybe 1 year, it will arrive inside the bandwidth of the interferometers. And the funny thing is that you can predict when it will enter in the bandwidth of the interferometers on the Earth, and also when there will be the coalescence. So to alert month before all the telescopes that there is a time in which they have to look in that position exactly. So this is, I think, the fantastic things will come out from that.
So thank you for the talk, first of all. I have to say gravitational wave physics seems to me like maybe the most exciting thing going on in physics today. I'm not in the field, so that's a genuine compliment. Frank, regarding your question, I want to make it both worse and better for you. It's worse because the wavelength of visible light is actually 10 to the 4 angstroms, not 1. And no. The wavelength of visible light is 1 micron. So that's 10 to the 4 angstroms. So resolving a displacement of 10 to the minus 18 meters means resolving the phase to a part in 10 to the 12. This is done using 2 things. Tell me if I'm correct. One is the finesse of the cavity, which gives you 100 bounces or so. That's a factor of 100. The other is using very careful single mode optics, so that when you put in a kilowatt of laser light into the cavities, there are 0 watts coming out the dark port. And a displacement of 1 billionth of a fringe gives you 1 billionth of a kilowatt coming out, which is relatively straightforward to measure. Is that a reasonable?
Why don't you enter in our field?
I love your.
You are welcome.
Okay, so, yeah.
On the slide.
Wait, because there are people online. This stairs is just for. Okay.
Again, thank you for the talk. On the slide where, near the slide where you were presenting the science case for the telescope, the Einstein Telescope, you mentioned lots of different things that it could do, one of which was Radioactively powered transients.
Power transient.
Radioactively powered transients.
Ah, yeah,
What
yeah,
is
yeah.
this?
Yeah. Well, you are right. This is because of the, you can distinguish the lines of emission of many nucleus for information. You have seen the brightness curve I've shown from the binary network stars emitting for days after the events. So you can detect the lines of the various nucleus and understanding also the isotopes with a large signal to noise ratio. In this sense, you are able to have hints on what happens that, from the point of view of the transmutations of the elements there, their process and so on.
Good, thank you again. We thank the speaker and
Talked about the localization of the electromagnetic